So welcome everyone to this IAS talk. My name is Martin Svensson. I am the chairman of the Department of Mathematics and Computer Science, which for those who do not know it is just in the vicinity upstairs and across the corridor upstairs here. So and I'm here today to introduce the speaker, Professor of Computer Science, Schneider-Kamp. So Peter was hired at IMAD, as we call the Department of Mathematics and Computer Science in Danish speech, in 2009, I believe. And since then, he's been around the university in many shapes and forms. Some of you may have encountered him in his recent role as the PI for the Codex project. So Peter's research belongs to a realm of computer science called automated reasoning, and I asked Peter to provide me a one-liner for what he's interested in, and he said, supporting the development of reliable data-driven ICT systems through automated software tools based on strong mathematical principles.
Perfect.
Yep, thank you. So applications of automated reasoning are, for example, software verification, hardware-software synthesis, and computer-assisted proofs. So today Peter will give an IAS talk with a title that is particularly relevant for me, seeing as I am myself a mathematician. Artificial intelligence, can computers replace mathematicians? Please go ahead, Peter.
Thanks for the introduction, Martin. I think this is a good place to say that the Department of Mathematics, when it integrated computer science, had some considerations to rename itself to the Department of Natural and Artificial Intelligence. So we're going to be on the artificial intelligence side, but we're going to take a look at the natural intelligence side too. And yeah, the title's of course a little bit provocative. Can computers replace mathematicians? And the good news is, before we start the talk, not anytime soon. Yeah. But, and there's a big but here. Let's first talk about how computers are not going to replace mathematicians. Yeah. They're not going to come in the form of robots holding chalk and drawing formulas on blackboard to prove new theorems. That's my prediction. Let's see. Time will prove me wrong. Yeah. So this is a very beautiful picture, but not exactly what we're going to look at today. Now, this is a lunch talk, and I hope you all got some food, or you still have some food. Yeah. So it will be served in 4 courses, the talk, not the food. Yeah. That's serve yourself. The first one being the smoking gun. That's coloring the Pythagorean triples. It's a computer-assisted proof, I can already tell you so much. And then I'll look a little bit more into what a proof is and how the computer can assist with that. And well, the challenges that we see there. And in the third course, the main dish will come towards a solution. And I'll wrap up by taking a broader outlook on what is happening outside of mathematical proofs in artificial intelligence, and how what we learn from teaching computers to do mathematics can help us with the challenges that we will encounter during the next 30, 40 years with artificial intelligence, before it becomes intelligent enough that it will take care of the challenges itself, maybe. Now let's start with the smoking gun, the coloring of the Pythagorean triples. This is also has gotten to be known as the 200 terabyte mathematical proof, the biggest proof by size of all times. And Marijn Höhle from the University of Texas, originally he's Dutch, and I probably mispronounced his name, he together with his colleagues got a supercomputer to produce this 200 terabyte proof for a simple conjecture. We'll look at what the conjecture is, but this draws a lot of attention because it's so large that we don't need to guess anymore. Can humans verify this proof or not? Now, what is a Pythagorean triple? Well, a Pythagorean triple is a triple of 3 numbers, a, b, and c, such that a squared plus b squared is c squared. Here's a geometric interpretation where we can see that c squared here is the same as a squared and b squared, because this is, well, these triangles here, they are identical, these are identical, and these two, and well, the blue ones also, if they're blue. And now the task here in this mathematical proof is to find out, given the triples until a certain number, can we color them by two colors? Let's call them blue and red. It could be black and white, whatever you like. Yeah, but blue and red, such that no triangle is monochromatic, meaning that no triangle has only blue corners or only red corners. And well, for the first triples, the ones until 20, we have these 6 here. Yeah, and well, as you can see, there are some interdependencies. If you color this one here red in this triangle, well, then it's also red for this triangle. And these interdependencies are what makes things a little bit complicated. There's of course a solution for this. This is one of the possible solutions, and you can see this one here has a blue and a red, this has a blue and a red, this has a red and a blue, this one has a blue and a red, and this one also has a blue and a red, and this one also has a blue and a red. Great. They are all not monochromatic, so we found the coloring of these triples. Now the things blow up a little bit when we come to all the triples until 7,284. Now this is a very good example of a computer-assisted proof which is very easy to verify, yeah, also by humans. Yeah, we have the numbers from 1 to 7,284, and the ones that are part of some triple after some symmetry reductions, they are either blue or red. And now we can just list all these triples. Yeah, it's many, but it's doable. A mathematician could do this in less than a year. Yeah, go through all the triples and check that by this coloring they are actually monochromatic. Yeah. So where's the problem? The problem is when we do the plus plus, when we go from 7,284 to 7,285. Yeah? Because then there's no coloring. Well, that was at least a conjecture, long time. No one has been able to prove that conclusively, but in 2016 they managed to produce a proof for this, and this conclusively, well, the claim has proven that there is no such coloring for the triples until 7,285 including. Now a 200 terabyte proof corresponds to 157 million and a few Bibles, yeah, standard Bibles. They are 13 by 3 by 18 by 4 centimeters and 4 centimeters thick. And if you lie them down flat and one after the other, this is a circle that goes through Toulouse, Sochi, where the Olympic Games were, and Toronto. Well, that would probably be the other way around. Yeah. So this is a circle of 28,974 kilometers. Yeah. Just to have an idea that each of them has 896 pages. Yeah. And it's very thin paper. Yeah. So this is really a lot of information. Now, one mathematician who would be really well trained could process this at a speed that would take 10 billion years to verify this proof. Luckily, we have a better option. We can train 100 million people to be mathematicians. This is consistent with some expectation about mathematical talent in the general population, yeah? Assuming that we will reach 10 billion on the planet. Yeah? So this is something like 1% of the population has a mathematical talent sufficient for this. Great. Then it will only take 100 years to verify this proof. You can scale it a little bit, yeah, but not much. So this is really infeasible. So this is a good question or good time to go back and ask ourselves, computer-assisted proofs, what does that actually mean, and what are the implications here in general? Well, I'm sure there are some mathematicians here. Who's a mathematician by training? Yes, well, there's a handful. Yeah, the rest aren't. Great. So let's start with defining what a proof is. Well, there are many ways of doing that, and I could probably talk 2 hours about this kind of question. But we'll say that proofs are witnesses for the truth of statements. So you have a statement which says, for example, there's no coloring for the Pythagorean triples until 17,285. Yeah? And then this can be either true or false. And a proof would be something that describes conclusively why this is the case. Mathematical proofs are based on logics, yeah, and they're often anyway given in natural language. We will see that you can also give them in a formal language, but most mathematicians don't go to that level. They also work a lot with their intuition and experience. Now, a proof is valid if the only assumptions that you made are axioms. That means you really have some very basic assumptions that are widely agreed upon, and that all the other statements that you just use without proving them, that they have been proven previously by other mathematicians or however, yeah, and that all the steps in your proof are logically sound. That means when you say, oh, this is true and this is true, and now I also know that this is true, yeah, well then this has to follow from some kind of logic inference. It can be induction, deduction, yeah. Now there are many ways of making proofs. Direct proofs, they just go and step by step prove what you want to prove. You can make probabilistic proofs where you have an argument, not that it is probably true, the statement, but an argument that shows that the statement is true using probabilistic means. Very interesting. You can use contraposition where you say, well, instead of showing that when we have A, we also have B, we show that when we don't have B, we don't have A. Yeah? This is also very popular. Induction, where you show that something holds for some elements, and then you have shown that when it holds for some elements, it will also hold for all the elements of something. And then finally, well, there's a long list more, but for us interesting, by exhaustion. That is when you have a number of different cases to consider, and you will just exhaust all of them. You will look at all the cases. So you'll say, for example, either this number is negative, or it is positive, or it is zero. And then you have three cases, and you exhaust all the possibilities. And as you can imagine, you can combine these strategies, and there are many more here. Now,
sorry, can I ask a
yes,
question?
of course.
Yeah.
You're all very
So,
welcome.
you know, Fermat last year. No?
Sorry?
If I consider the Fermat last year, last
Yes.
year by Fermat.
Yeah.
So it was attempted to do it be done with computers,
Yes.
but was never been able to prove whether it was actually true or not. Right? So, and then the formal proof without computers opened up an immense amount of new mathematics. I'm challenging it. So what would you consider really better proof? The one that's been done that opens up an immense other possibilities, or a proof by exhaustion?
The question is, do these need to exclude each other? But
No.
exhaustion is, of course, not feasible in case you have an infinite number of cases, like this case. But of course, Andrew Wild's proof and all the work that he built on that gave an immense boost to a lot of areas of mathematics.
Would you agree that it's actually good to have actually a hint from a computer? But
This
it's
is
so much better to have actually a full, full proof without a computer.
We'll come back to that in a moment, so I don't want to take too many proofs ahead. But yes, one of the first proofs that was done with computers, and the one that has widely become known as the first computer-assisted proof, although there were some other small things that were proven with computers before. That is the four-color theorem, and this is saying that any map, so any planar surface divided into some kind of other surfaces, can be colored by four colors in such a way that two neighboring surfaces don't have the same color. And this was first conjectured by a guy called Francis Guthrie, or I have no idea how to pronounce his name. And it was finally proved in 1977 by Appel and Haken. And the fun part here is that a lot of people have tried in between, in the years following the original conjecture. There have been several proofs, and two of the proofs that were not immediately debunked, they actually each of them survived for 11 years before someone found a mistake in them. Now, how did Appel and Haken finally do this? Well, they first made a reduction to a finite number of cases, and this is based on deep mathematical insights, and it has been done by hand. Basically arguing that any smallest counterexample to this, so any map that needs 5 colors, you can always make a smaller map until it can't get smaller and it's not anymore a counterexample. And if you consider only those, then they have to contain one of these cases. And there were 1,936 of these cases. So what they did is they programmed the computer with these cases to go through all of them and color these maps. And the result of is 400 pages of microfilm that are at least hard to verify humanly. And the biggest question, of course, that everyone started asking is, can we trust the computer program? Well, at that time they also asked, can we trust the hardware? This is still an issue of hardware, but less than it was back then. Yeah. Now, some of the questions that come with this, they are whether mathematics is actually an empirical science or not. Yeah. I mean, the statements, they are only true mathematical statements that we want to prove if they hold for all cases. Yeah? So empirical confirmation that we tried for a lot of cases and it always worked. This is not enough to prove that the statement is true. Now there are different views on what mathematical truths are. The Platonist view is arguing that truth is something that exists. Mathematics is abstract and exists without any preconditions, and all true statements, they already exist. They just need to be discovered. Yeah? So this is putting mathematics on the same level as astronomy. Let's look what kind of stars we have out there. Let's go and find a proof. Yeah? While other streams, they are saying that there's no a priori knowledge and all mathematics is a result of empirical evidence. For example, the fact that 2 equals, 2 equals nothing else than 2, but 2 plus 2 equals 4. Yeah? This is something which we empirically learn. We take 2 things, we take another 2 things, we put them together, we count, and they are 4. Yeah? And that's a little bit the other side of the camp. And of course, as usual, there are many camps. There's the logicist camp, and then there are the constructivists. But the main thing here is that, and now we're coming a little bit back to the question about the insights that the computer can generate, that you can actually make experiments on mathematical statements and see whether they hold. If you find a counterexample, you have disproven the statement, you actually know that it's false. And if you don't, and you have been trying hard, then maybe you have gotten some idea that it holds, and then maybe you can actually try to use the empirical behavior of something to get some insight into how the mathematics works and come up with new theories for that, or also generate new statements, new things that we could be interested in whether they're true or false. Yeah? So experimental mathematics, where you use basically experiments, and nowadays you would do that with computers, yeah, to check the statements for truth. They are a way of turning mathematics into a more empirical science. Well, this is a good thing or a bad thing, we're not going to find out today, but you're very much invited to come with some views on that.
But wouldn't I call it more trial and error than experimental?
Sorry?
In experiments, you do an experiment.
Yes.
And either you get a false or a right answer, which is okay, but it's actually nature.
Yes.
So I can have 10 different models of nature, one is going to be right by experiments.
Wow, one might agree with all.
Is that more trial and error? It's more like trial and error. I mean, you try something, and it might be wrong, the statement. Is that trial and error mathematics rather than experimental mathematics?
Well, at least it is where you start. But the proponents of experimental mathematics, they actually argue that by doing this, you mimic what every mathematician is anyway doing. Mathematicians are going and thinking, could this hold true? Let's try for some values.
I understand whether a better name is not experimental, but just basically trial and error.
Trial and error. Well,
mathematics is either true or not.
But also with experimental sciences, if you think about theories, yeah, you can say whether it's true or not.
You're going to be careful with that.
Oh, well,
you cannot compare.
Let's go and have an experiment, and then we can see whether Einstein was right or not. Yeah.
No, you
well, then you
different tiers to actually the same experimental truth. That's different things. Here, mathematics is always true on its own.
That's a view. Yeah, that's the Platonist view. Now, how do we get out of this mess? Yeah, we can. This is a good mess, but still, we need to somehow be constructive. Well, in the after math of this proof by Appel and Haken of the four-color theorem, one of the critics, Tymoczko, he said that the proof is something that he would consider non-survivable, and he was then stating that he thinks a mathematical proof should be convincing, surveyable, and formalizable. Yeah? Where convincing means that it should convince you that it actually proves what you want to prove, that it actually has a connection to the statement. Surveyability means that as a human you can go and verify the proof, you can understand all its parts, and you can go through all of them. And the formalizability, that you, at least in principle, can break down all the reasoning that happens in the proof into small formal parts, formal operations in logic. Even if you didn't do that, but it should be possible. And he was criticizing Appel and Haken that the proof of the four-color theorem, it's not non-surveyable, it's not feasible for humans to go through all these cases and understand whether this is all correct. And he also had some doubts about formalizability, whether you can go and formalize this proof. Before we come back to formalizability, we come to another conjecture, the Robbins conjecture. And this is on something that computer scientists love, Boolean algebra. And one of the sets of statements from which, or axioms from which you can derive all of Boolean algebra, that is associativity, commutativity, and this nice equation, which is, whoa, it's not the Huntington equation, that's the Robinson equation. Yeah? And now, some guy called Huntington suggested that we use this one instead, and Robinson, and then he said there would be a new kind of algebra from this. And Robinson, who actually came up with this equation, he said, wait, I would conjecture that this equation here, together with associativity and commutativity, will give rise to the same algebra, to the same Boolean algebra. Well, it took until 1996 for a proof of this to be discovered, and it was discovered by an automated theorem prover. That is a first-order logic-based theorem prover where you can give a statement in first-order logic, and it will give you a proof, maybe or maybe not. Yeah. In this case, it was able to prove that. And well, there's a lot of questions that come up here. One is whether we can trust the computer program, this prover EQP. And of course, the answer is we shouldn't. Yeah, because it's a software, it has bugs. Yeah, it evolved later into a tool called Otter, which is still very competitive. And well, I've seen how this has had bugs in real-world competitions. So this is not what we can do. Then, what about human verification and human understanding? I mean, we would like maybe not only to have some kind of formal proof discovered, but would also like to understand how this proof is actually built up and what kind of theorems and lemmata this corresponds to. So what happened here is that McCune.
Sorry, maybe you already said that, but I was told when I was a kid that they can never construct an automatic demonstrator of theorems because you have always a famous enunciator that you can never be able to prove, like are parallel lines parallel, right? So then you need actually a hierarchy of computers to be able to decide on that. A famous example, I can have a perfectly well-defined grammatics, and I'm going to make a next statement, we say I'm a liar, decide. What will the computer do? I know that actually it's impossible for a computer to do that unless it's an external input and decides whether the next postulate is part of the postulate or is a part of the demonstration. Isn't it true? That means that from the very beginning you're flowed. So how do you do that?
Well, I mean, the idea here is that this only works in some cases. I mean, either you take a logic that is associated.
Oh, I'm going to be paid, but I want to understand.
Let's take propositional logic, yeah, where you just have propositions and Boolean operations on them. There, things are decidable, yeah, and you can actually, if you don't care about how fast it is, you can go and decide the truth of every statement.
How does the computer knows whether I'm a liar or not?
Well, this depends on how. This depends on
given the set of the grammar rules.
Yes.
It's perfectly well-defined grammatic statement to say I'm a liar.
Yes.
However, is it false or true, the statement?
Yeah, but I mean
This
this.
example in logic that you actually cannot decide unless you have a friend telling you whether it's right or not. That's a famous #1 example of undecidability.
Yes.
That actually throws a computer off his own,
But this is a
chip. So how do you do that?
Well,
It's
this is a problem when you consider that you either want to have a general artificial intelligence or when you actually don't.
I mean, that particular energy change could be part of your postulate or can be proven. Either way, you don't know. But if it's not possible to be proven, the computer will never be able to find a solution.
And that's fine, because
I
I mean.
decide one. That's fine.
Oh,
What is your statement for that's fine?
That's fine. It's exactly. It's fine if I can prove the statements that I want to prove.
So you know them. So you
Oh, let's say
a priori you don't need a computer.
Let's just say, actually, if we go away from this concrete question to my research, I'm doing a lot of software verification, and it's been shown that it's undecidable whether two functions that are implemented in different way behave the same for all inputs. Yeah, it's undecidable, but that doesn't mean that you can't do this in concrete cases. In normal, interesting concrete cases, which have not been constructed to be paradox or to demonstrate some kind of undecidability, this works. Yeah? So that's exactly the same here. This automated theorem prover cannot show all the theorems. That's okay, because it can show some theorems that we're actually interested to
So if I
prove.
understand correctly, so what you're saying, I'm trying to understand,
Yeah.
because I know that it's impossible to build one. So and from what I heard, it seems that you could. So the truth is you can, but they're actually, in certain cases, useful. Is that correct?
That's
Okay.
a good
I
summary.
agree with that, but
Yes.
I mean, I know theorems cannot be violated, so you cannot construct something you cannot construct.
Oh, don't worry. I'm solving undecidable problems every day. That's a part of what we used to say when I was a PhD student. Yeah. What is the undecidable problem of the day? Let's take a decidable fragment which is relevant for our problem. Let's solve that. Yeah. And then we just have to care about efficiency, which is another beast which we're not getting into here much. Good, but actually someone sat down and produced a proof, human readable, with lemmata and proofs, and then a theorem that is proven based on the other lemmata and theorems that had been proven before. This is still not very easy to survey, but you can follow. This is a paper of some dozens of pages, and I've actually looked through that just to be sure that I would consider that surveyable. So in this case, it was still possible to go and take the output of the computer and with a lot of work formalize this in readable mathematics. Now, what are we going to do in general when we're thinking of our smoking gun, of the 200 terabytes proof? Yeah? This is not going to work for the 200 terabyte proof, because it will take 10 billion years to go through it for a mathematician. So it will take even more time to make a paper out of it. Plus, they'll have a problem with submitting the paper because they're usually size limits, page limit or size of the file or things like this. Microfilm is not a solution either. Now, what is the solution? Well, the solution is to use formalization and then rethink things a little bit. And we'll take this in 2 steps. We'll start by looking at formalization. Well, if you formalize the proofs, then you describe them in a formal language where you have axioms, you have assumptions, and you have inference rules. And then you syntactically apply the rules, and then you can get from your axioms and your assumptions via the inference rules to the truth of a statement under these assumptions. Yeah. Now, as we already have been input, this cannot always work. Yeah. There are, for any interesting logics, there are things that you can't generate by this. Well, people would disagree, but they would find some logic that they think is interesting, but
That's a
for
theorem, actually. Undecidability. So any axiomatic definition of mathematics contains always axioms for which you cannot be decided upon. It's a theorem.
yeah, if you have enough axioms that you have enough power to
Then you
do
can-
interesting mathematics. The question is what you would consider there to be interesting. I can take propositional logic. It's maybe not interesting enough to axiomatize mathematics, but some people find this interesting. Now, finding proofs, even if they can be made in this way, is usually very hard. Yeah, because there's a whole space of possibilities to explore. I mean, all possible inferences that you can take at some step in your proof, and then this is branching. At each step, you can do a lot of different things, which means that, and you don't have a limit on the size of the proof. Yeah. So this is really infeasible for many things, even if it worked for the Robbins conjecture, which is a really, it's a really small thing to prove here compared to some of the other things that you might want to prove. But we observe one thing here, that checking proofs is usually much easier than finding them. Because once I have a proof, for example, up there is a proof that, well, starting from the axiom that Socrates is a man, and, well, the other axiom that you can either be a man or a mortal, and the assumption that Socrates is not mortal, yeah, you can actually reason yourself using inference called resolution, yeah, to that Socrates is mortal, and then another step to that the assumption that Socrates is mortal is actually false. Yeah? And by this you refute actually this statement. So you can use this to prove or disprove statements. Yeah? And now finding this proof can be much harder because you have a lot of things that you know, and it can be a hard way to build this kind of tree which will end in true or in false. Yeah? But checking that is not so hard. You just need to go and then check, are these axioms or assumptions, and then are each of these steps here okay? Now we had some doubts about can you formalize the four-color theorem? Can you represent that in some kind of formal system? They were voiced after it was presented in 1977. Well, this is something that Gontier answered in 2008. Well, actually, he did the work earlier. He started in 2000 and I think finished in 2005, but that's when the journal article got accepted, yeah, and published. Now, first he tried actually to prove the computer program correct that Appel and Haken had used, because this was the biggest issue. The biggest issue was not the proof of you can reduce it to 1,936 cases. The biggest issue was once we have these 1,936 cases, did the computer really show that all of them are okay, that they all can be colored by four colors? Yeah? And well, he found out that this was very hard and that anyway it would not give the full proof. So instead, he made a full formalization in the theorem prover Koch. Well, he did the formalization of the reduction. People had worked on this in the meantime and had found better ways of reducing it to fewer cases. So he could actually formalize the reduction to 633 cases. And he made a proof, a formalized proof, that these cases are unavoidable. That means whenever you have a smallest counterexample to this four-color ability, so something that would need 5 colors, well then it has to contain one of these 633 cases. And then as a third thing, he formalized that all of these 633 cases are four-colorable. Yeah? Now, the good thing of doing that is that now we don't need to trust some strange program written by Appel and Haken in 1977, but only yeah, the interactive theorem prover Koch. Well, Koch is based on the calculus of inductive constructions, and it has a very, very small kernel. It's like a one-page of code, approximately understandable code, and this has been by hand, and I think later also formally, using another theorem prover, been proven to be correct. And if this piece of code is correct, then it does not accept proofs, for example, the full proof of the four-color theorem, which have any flaws. Yeah? So we have reduced what we need to trust to a very small computer program. Yeah? There are still discussions about what we still need to trust. We need to trust the program that compiles this. We need to trust the operating system and the hardware this runs on. But this can be mitigated a little bit by considering to run on different hardware using different compilers. Yeah? Well, also by that these theorem provers like Koch, we will see another one, Isabelle soon, have been used for many, many problems, and they are very well checked. So in this way, we have increased the trust, although of course there's no final certainty. Now another proof, relatively famous computer-assisted proof, is the Kepler conjecture, and we'll see in a second why I'm starting to talk about this. But what is it about? It is about taking spheres, let's call them balls, yeah, and packing them as tight as possible in three-dimensional space. Yeah? And the conjecture was that there are two different packings which are both optimal, the cubic close packing and the hexagonal close packing. And they are represented here. Yeah? And these two packings, they are both optimal. And well, this is something that Johannes Kepler conjectured in the 17th century, 16 something. Yeah? And Thomas Hales finally, after many, many people tried for for 300 years, yeah, has proven in 1998. And the referees of that article, they were 99% sure, they wrote in their reviews, yeah, that the proof is a proof. But they weren't entirely sure. Yeah. So Hales then started a formalization project, which he estimated to last for 20 years. Yeah. Luckily, it was a little bit faster, so he started in January 2003 and finished in August 2014, 13 years and 7 months, yeah, for formalizing the proof of the Kepler conjecture. And they used another interactive theorem prover, Isabelle Holl, which is well, less French and more German. I'm not going to say more. That's I know the guys behind both of them, yeah, so I have to be careful where I'm treating. I'm usually using Koch, but this is also an excellent and very trusted theorem prover.
So the 99% suggests, of course, that there's a certain amount of intuition also going into evaluating.
There were steps that the referees thought were logically sound, but that they could not really argue down to the level of formal logics, yeah, where they were saying, I believe that this is the case, but I'm not sure. Yeah, and well, the formalization took care of all of that. This is probably one of the most ambitious formalizations in terms of size of the formalization, not in terms of the size of the proof. Yeah? Which brings us back to our goal to verify the 200 terabyte Pythagorean triples proof. Yeah? Or to formalize it, or to somehow be sure that what these crazy guys in Texas did, this actually constitutes a mathematical proof. Yeah? Now it's infeasible to formalize the proof, because the proof in a very compact representation takes 200 terabytes of storage. Yeah? Putting this into some kind of formal logic will blow it up to petabytes of size, and there are no theorem provers, automated, interactive, that are able to deal with proofs of several gigabytes. Yeah? There are definitely none that can deal with terabytes. Yeah? And petabytes is completely off the chart. Yeah? So we had to come up with some good idea how to do that. And after reading about this proof, my colleague Luis Cruz-Felipe and well, I was visiting a guy in Portugal. He's a professor there who's actually working on satisfiability of propositional logic. Yeah? We were also discussing this proof, and we really were like, okay, we need to do this. Yeah? This is really something that we don't believe this. I mean, maybe it's right, but this is not a proof. Yeah? And this really stretches the limits too far. So what was the idea that we came up with? We came with the idea of saying, instead of trying to formalize all the proof, yeah, let's automate the surveying process, the process of going through the proof and checking that the proof is actually a proof. Yeah? And well, that means formalizing the process of proof checking. Yeah? Having a proof checker which we then prove using Koch or Isabelle or another interactive theorem prover to be correct. And use this proof checker to find out whether these 200 terabytes are actually a proof of the Boolean Pythagorean triples conjecture, as it's so nicely called, or not. Yeah? And well, to handle the 200 terabytes, we then had to tune both the proof and the proof checker for efficiency, meaning we actually blew up the proof from 200, just under 200 terabytes to nearly 400 terabytes, adding extra information. Imagine like when you're doing mathematics by hand and you you can have some kind of intermediate calculations. We added this kind of intermediate information to the proof, yeah, such that the steps would be easier to verify. And well, then we did some more standard computer science optimizations on the checker and proved again and again that this is still a valid proof checker, that if this proof checker says these 200 terabytes are approved, then the 200 terabytes are a mathematical proof of the Revolt's conjecture.
So technically you made a referee. That's the first automated referee.
Basically, it's an automated referee,
cool.
yes.
I mean, finally get rid of people, we don't have to waste time anymore refereeing people.
It's unfortunately not going to work for all problems, but it would work on this Erdős conjecture that was proved in 2014 with a 47 gigabyte, or 4.7 gigabyte, I don't remember, proof. Yeah. Now, having done that, we were actually able to use a supercomputer, yeah, with this fully verified, formalized proof checker running on many of the nodes of the supercomputer, on many of the cores in there. Yeah. And then in 1,378 CPU days, we actually redid the proof independently that the Texan guys did and tuned it to blow it up to this nearly 400 terabytes. And then another 2,608 CPU days we verified using this automated mathematician, if you want, the automated referee, yeah, these 389 terabytes of proof. And well, given that Abacus is a pretty nice supercomputer, the runtime for all of this was on the order of 4 days, I think. 2.5 days for this, less for the first step. Yeah. So that's nice.
You go from 4 years for refereeing to 4 days.
See? Yeah, or from 10 billion years to 4 days. To 4 days.
Yeah,
yes.
Yeah. Pretty cool.
And well, so the artificial mathematician then.
Would the journal pay for the build of Abacus?
Abacus was not in the journal.
The referees are free, yeah. But are these?
Oh, this is from an article in Ingenieuren where. Well, this was before we.
No, I mean whether this is marketable, whether the journals would love to pay for referees that can give an answer in 4 days. That's paid for running a supercomputer.
Well, given that it requires the proof to be in some machine readable format that the referee can do, but yes, that would of course be nice. It is in general the question of how are we going to handle the increasing number of computer-assisted proofs. Yeah, that is a discussion in the community, and it's discussed in the mathematics community where people do computer-assisted proof. It's also discussed in the proof theory community. It's discussed in the automated reasoning community. So there are many communities where they have all the different views on this. That's the nice part, of course.
A question on that, I was thinking about verification.
Yes.
So, have you used known proofs as verification? For example, a Hilbert proof or something like that. So you actually say, I can verify the program works by showing on known cases the computer can actually complete the same proof. You use this at all?
Not in this case, but it could be used. Yeah.
Do you use it?
No.
Okay.
So this is completely bottom up. Yeah. The only thing that we're using is the correctness proof of the calculus of inductive construction. Now, well, I mean, actually, this is a good place where I can ask you if you have any questions to the 200 terabyte proof or its verification, because afterwards I'm going to broaden the focus a little bit.
So when you send
So wouldn't you need actually a reviewer of the reviewer? I mean, according to which is actually Francisco's point.
A review of the reviewer. So you would say, who would
a checker for the checker.
Who would check the checker?
Yeah.
Well, that is the good thing that with this checker is that this checker is of course being published in a journal right now, and I think it's accepted for publication, and it has been going through a reviewing process. Yeah.
Yeah, but then also the algorithm was published. I mean, the first proof was I mean, it's a published algorithm or a published thing. I mean, so it's, I mean, You can always say, I mean, I
Yes,
don't
but,
trust it.
I'm 100% sure that the referees of the original article with the 200 terabyte proof, they did not survey the proof. I'm very sure on that. While I'm pretty sure that at least some of the referees that we had for our work here have read the entire checker. Yeah, because they actually came with some.
But in principle,
good,
when should we stop? I mean,
remarks.
so, I mean, so there's a logical problem.
But that logical, can you prove something that wasn't correct?
Yes, that is, I hope we can't. No.
You hope you can, but I mean the question is, no, make sure that the checker is correct. You should also check that if I have a wrong proof of something, that
Yes.
actually checker
Okay.
shows that this proof is wrong.
I mean, what we can guarantee is if the checker says that it's a proof, then it's a proof. This is the only thing that we formalized and proved. We did not prove if it says that it's not a proof, whether this is actually the case or whether it can still be a proof. So only in the case of a affirmative answer, there we have a guarantee that it's a proof.
I mean, since I don't know anything about
Yes.
your specific paper, so first one, but can I ask a specific question?
Yes.
When you say proof is a proof, it could also just mean that it's not proven to be wrong, but doesn't mean that automatically it's right.
Yes, but in this
There's a
case,
possibility, right?
yes, and that's exactly what we are doing. We're not looking for counterexamples and saying there's no counterexample. Yeah. We are, in this case, it is really a resolution proof on the level of this one here.
So the logic is correct.
The logic is correct.
It doesn't mean the proof is right. I
No,
can have a logically correct statement,
Right.
but that statement not need to be right.
right, but the statement,
So you like another referee.
but we have the sequence of inferences
Yeah.
that are made, and this is actually what constitutes the 200 terabytes. And the whole point is that we go through all these 200 terabytes of inferences and check each inference. Yeah. And what is nice here is that it is really a very simple piece of code that is actually making this check because we put in all the intermediate, wrong one, all the intermediate information into the proof. Yeah, which means this is really as difficult as saying, well, it's basic set theory where you have addition of one element to a set and you have set difference. These two operations. That's the two only operations that the checker needs for this proof.
How independent on the specific proof it is? Imagine that somebody comes with a different or something.
The answer to that is it's completely dependent, but yeah, there's more and more proofs which use a set solver as the means of actually finding a certificate or of showing absence of exhausting a search space. And all the ones that use a set solver, we can use this for. So for example, this Erdős conjecture, we could also verify that it was just not as impressive as the 200 terabytes. So the answer is if you use a set solver to exhaust the search space, then our checker can, without any extra work, give you a guarantee that this exhaustion was correct. It will not tell you whether this exhaustion in your proof context has any other meaning than that. This is something that we needed to do additional and also which was specific to the proof, but this was something that took a couple of days to do. Good. Now the dessert, where we are leaving the mathematical proofs and we're coming generally to artificial intelligence, and I called it taming artificial intelligence. Well, this is maybe a little bit over the top. It goes the same direction as any reasonable, well-behaved Terminator movie. Yeah, machines starting to fight with us. Yeah, but there are some much more real problems. Or this is actually something that can happen also. But this is actually what I'm looking at here is much more on the line of automation of human labor and machine learning. Let's start with the automation of human labor. Yeah, this is an old but very nice article where, well, which you can say is completely unreliable, and no one has proven that this is true. Yeah, but this is an estimation of which jobs have what kind of probability of being automized here or not being automized within a certain time frame. I don't remember how many decades, but not many. Yeah, and as you can see, this management and engineering and education and these kind of things, they're on the low probability up here. Yeah. And then there's a high probability for all these service things, sales and service and administrative support and yeah, these kind of things. And then there's a middle ground with also a lot of potential for the more physical jobs. Now, how does this work? The oldest way of replacing human labor is probably by using expert systems. Yeah, this is one of the first success stories of artificial intelligence, where the idea is that you look at human reasoning processes. How does a doctor diagnose some kind of medical condition based on symptoms? Yeah, well, he goes and he checks, does it have these symptoms, and is this blood value over or under this value, and so on. And these systems, they mimic this kind of reasoning. And this has been very successful in clinical decision support. This is actually only now being rolled out on a wider basis in different countries, but it's has been, people have been working on this for 40 plus years. Yeah. Credit risk assessment, piloting some kind of aircrafts or boats or whatever automatically, yeah, where depending on what kind of conditions you find, you have to make different decisions. Yeah. This is challenging for humans to verify whether the decisions made by these systems are good, but it's not impossible. Yeah.
Right. I mean, when you say successful, do you mean that it is used more and more? Or do you mean that it actually improves? For example, credit risk assessment.
Yes.
It's not clear that it actually improves the risk assessment, but it is clear it is used more and more.
Successful in the sense of this is being used more and more. Yeah. I'm not going to judge whether that's a good idea or not. We can say that it's successful also in the sense of that it gives really good results when we look at autopilots. Yeah, they can do amazing things. Yeah, but one can also argue about that. And credit risk assessment, I'm more skeptical myself too. Yeah, the clinical decision support is mostly a matter of how much the persons do actually rely on this. Yeah, versus blind faith versus using this as a supportive tool. Yeah, so that's of course in the applications this is hard to judge. But what is possible here is, even if they have a lot of knowledge in there and a lot of rules and stuff, you can always come with a trace saying that I say that this person should be tested for diabetes too because of these and these reasons. That's why the system came to this conclusion. Now fast forward to 2014 plus, that's where we're living. Yeah, closer to singularity if you believe some, far away if you believe others. Machine learning, this is one of the new blacks. Yeah, and there are two mainstreams have been for a long time. At least when I studied this in Trondheim in 1999, there were already these two streams. One based on statistical learning, yeah, and one based on neural networks. Yeah, and in both cases you get correlations and you get some interesting effects without actually understanding what happens in there, without getting some explanations. And this is also gaining traction in many fields. That is the way success is measured. Yeah. So this is used a lot in big data analytics for predictive maintenance in autonomous systems. You look at the Tesla cars when they're autopiloting. They're doing this not based on expert systems, but on autonomous systems. Yeah. And kill the F. And currently, it is not feasible to formally verify what such machine learning-based artificial intelligence systems tell you. So if this artificial intelligence, even based on deep learning with the neural networks that take care of the feature extraction and whatever, if they tell you the best decision in this case is to do this, yeah, then you don't know why it was deciding like this, and you also have no way of verifying that this is actually a good decision versus there's something wrong in the neural network simulation software or in your statistical learning package. Yes?
Is verification strictly necessary in all cases?
No, absolutely not. Thanks for the question. I had this on the slide. I'm not sure it's coming now, but verification is interesting in safety critical applications. Yeah, is it human health or is it flying a plane not into some mountain? Yeah, there's also a demand for validation, verification from laws in many countries. Yeah, but of course, if you just want to have some prediction on when to go out to your windmill and replace some parts in order to avoid that it breaks down, and you have to unscheduledly fly a helicopter there on Sunday evening, yeah, then of course you're welcome to just believe into the system. Yeah, but the question is, if you have an application where you need to verify this, how are you going to do this? Before we come back to that, I have a short look at the future. And well, there's this widely held view popularized by Ray Kurzweil, is it Ray Kurzweil? Ray, probably, who has been claiming for quite some time that the reasoning power of machines is going to exceed the ones of humans at some point of time in the near future. And currently the prediction is on 2023. Yeah. Has been on earlier dates before, yeah, and on later dates also. Yeah. And then this will accelerate the growth, because then when we have human level intelligence, the systems can improve themselves. Yeah. And this is all based on the exponential.
Trump, right?
Sorry?
This doesn't take into account Trump.
No. And this is all based on this exponential growth of computing power that we have been observing in the last many decades, last 40 years actually, yeah, known as Moore's Law. Now, Moore's Law basically states that the number of transistors per area doubles every 24 months, and then in a newer version that was corrected to 18 months. Yeah, but it has been taken as an exponential growth in computing power. Now, since the last 5 years, we have been starting to question whether this growth actually will continue. And if you look at the numbers and start making some regressions here, you can see that actually the clock speed of the transistors and also the power that is used are starting to level off to a certain degree. And there's still the transistor per chip, which is looking quite well until 2 years ago, but this is also starting to look non-sustainable. So there are, I think, 3 more scheduled generations of shrinking that Intel and AMD have on their plans, and then they're really hitting some hard limits like the size of atoms and things like that. Yeah. So we already hit the wall of increasing frequency using excessive power and giving problems with distances, because the speed of light is finite, it's fast, but not infinite. Yeah. And now we are also going to get problems with the number of transistors. So it's a little bit unclear whether we will see this growth over the next 40 years that we've seen in the last 40 years. And so the predictions here, they can also look much more conservative than Kurzweil's fantasies. We will find out what happens here. I'm personally somewhere in the middle. I think we will see an increase, not necessarily only based on hardware, but also on better use of this hardware, on better algorithms and new insights like deep learning, which really gave a push compared to neural networks before. Now, what's next on my agenda? What is the idea that I'm currently pursuing? Well, that is automating the verification of artificial intelligence. Yeah, there are situations where you need safety critical systems or systems that need to be reliable. But there are also other cases when, for example, administrative decisions are made, where the law mandates that these decisions need to be explained to the citizens. For example, if a system at the municipality will say that this person should not get more than this many crowns in what is content yield called? Good question. Yeah, in unemployment insurance is the wrong word, that would be, I don't know, let's say in unemployment insurance, yeah, there's some kind of decision like this made by machine learning. Yeah? We need to be able to explain to the citizen why was this decision made. Yeah? And in general, if we accumulate all kinds of knowledge by finding correlations and training neural networks and these kind of things, we know a lot, but this knowledge is tacit. We can't really get insights from this knowledge. We can't use this knowledge except for what the system has been trained to do. And that's why one of the things that I'm interested in, and whoever else thinks this is interesting is very happily invited to join me on this course, to go and verify or explain the decisions made by artificial intelligences based on machine learning. And well, of course we will need, this will be a big task. These are big systems with a lot of data. Yeah. So the ideas that we used to verify these 200 terabytes of mathematical proof, I want to take these ideas and use them to build some kind of artificial intelligence that can actually look at the results of machine learning and gather insights or explain what is happening there. So basically AI to help us understand AI. Thanks for your attention.
Thanks for a very nice presentation and answers. And any questions?
Of course.
Well, if you look at proof verification, we shouldn't be too surprised because mathematics is done exactly so that we have constructed proofs to be verifiable.
Or
by
non-constructive proofs.
Yes, also that. But then, if you look at how a mathematician would work, it's very unclear. I mean, you have true statements that are not provable, and you might not be sure about your foundations. So I don't still see how we could be replaced by computers. How does a computer take a question in number theory and solve it?
Well, there are two questions here.
Yes.
One is coming back to this one. Yeah. Well, the mathematicians, that's this one here. Yeah. They're the ones with the low probability of unemployment. And as I said, this is also a provocative title. Yeah. I think we should think of computers here as helping us in certain situations also of generating new statements and insights. But this is not going to replace us anytime soon. I mean by us, the scientists. Yeah. We are probably among the safest in this regard. Yeah. But yeah.
Probably.
That's probably. Yeah. Not all scientists.
It's probably like the way you think.
Yes, we're not going to go on that. But the second part of the question is, can a computer go and prove something about number theory? Well, yes, yeah, there are systems that can do that. Question is, are they going to prove anything that is so interesting that you find this worthwhile and you wouldn't have been able to do it yourself? There have been a few cases very well publicized then, yeah, where computers have found interesting proofs that humans have not. Yeah, but if it's more about the complexity of the proof, but not the complexity in size, but complexity in hardness, I think we still have the edge. Let's see how long.
Yeah, I'm interested in possible applications of an artificial intelligence in government and in the upper echelons of how power is sorted. And how far do you think, well, could there be a difference between a computer as a tool and a computer that gives us orders? Not necessarily in a tyrannical way, but in more like an operating system that can teach each generation what the generation before them knew, sort of like a grandmother, right?
Well,
You know what I'm talking about? You know what I'm trying to say?
Yes, I know what you're talking about. I would say that, well, I mean, we are getting there. I mean, machine learning based artificial intelligences are being rolled out in administration. They are being rolled out in a lot of business contexts now, and I think the more this will become standard, we will also see this, for example, in educational constructions, and then you know, once we will start letting computers support teachers in the schools, yeah, in a way we're already doing that, but by more intelligent computer programs, yeah, they actually can go and see what does the student understand and present it at the right level, yeah, and actually have a dialogue with the student and to teach. Well, from there it's not a long way to the scenario that you're talking about, because if we will find that the computers are becoming better and better at doing this, yeah, we will start letting them teach us in universities. We'll start letting them take decisions in first administration, then in the executive branches also, yeah. And then of course there's the whole long list of questions which are, how can we prevent them from becoming evil? Yeah. There's a
Maybe
I don't know.
if you ever been in a driverless, you know, a car without a driver,
Yeah, no,
you're already in the hands of artificial intelligence.
and it,
You live your own life in the hands.
Right, but can we replace the politicians with computers?
That would be nice.
Already now.
personally that would be my goal. But we first have to figure out how we prevent them from going evil. There was this case of this machine learning based AI that was learning from on Twitter, and then it became really, really nasty. Yeah? And I don't want this to happen to even the AI in a self-driving car. I mean, we have enough problem with terrorists of all kinds of colors to drive into people. Yeah, we don't need an army of
There's a question.
self-driving cars. Yes.
I mean, it's somewhat related to this discussion, so I was thinking it would be nice if you have, if not a proof, but a structured statement relating to which classes of problems that computers can solve and which classes they cannot solve or they're not very efficient at. There are some hints. Some colleagues in Aarhus, well, fair enough, but there's some hints. Some colleagues in Aarhus published an article, Nature, fairly recently that said, okay, the computers are very good if you define with some structure a problem space and let them loose within that. But with respect to discovering new problem spaces, they suck bigly.
So far.
And the question is, are you or anybody else making any attempt to curb your enthusiasm by looking into to a theory about what problems it can solve?
I think there are people who are looking into that, but I personally I have not been looking into that much, because I'm actually not the one who is going and letting AI loose on lots of problems, whether it's a good idea or not.
Sorry,
I'm just saying that from my perspective, yeah, the interesting question is when someone is using artificial intelligence to put their lives into that hands in a self-driving car.
Example, for example, very practical example. If we are at university and there are some strategical funds to be put somewhere,
Yes.
could artificial intelligence, based on how quality the researchers here are and what they are, actually distribute the funds so that actually the funds are given to the high-impact researchers?
This is
Thrown out of the window?
there's this is a very concrete question which I would answer that this is probably not the best allocation. It might actually find another allocation that has a better impact. No, it's the one where we don't favor the high impact researchers who already have funding.
Yeah.
I think we sort of skipped the beat because we went from you describing how they can solve the problem
Yes.
to them being able to identify the problem in the first place. And I think that's also sort of your question.
Yes.
That there is also like some creativity which is important, because coming up with a good solution and actually going through the entire data set of finding these knots and seeing if they're monochromatic is one thing, but stating the theorem in the first place is also an interesting question, I suppose.
That's
Now-
probably the most interesting.
Yes, and you're not a neural scientist, but so it's maybe more a philosophical question. But do you have any idea if this is possible to go from the specific case to the general case?
I am pretty sure that this is possible. Yeah. The question is, when are we going to see this?
Mm.
Yeah. Are we going to go extinct before? That's yeah. But okay, without that side remark, it is. I don't believe there's any general thing in the way for us to go and simulate or model or somehow in another way perform similar kind of activities than the human brain does. Yeah? So in this way, eventually we will get to a stage where we can simulate the human thought process or something better or similar. Yeah? But this is of course way beyond what we will see in the next couple of years. Yeah? There's this distinction between artificial specialized intelligence and artificial generalized intelligence. And what we're seeing right now is that at least for the specialized intelligence, just by raw computing power, we can get systems to do any task that is somewhat structured better than humans. Yeah? And tasks that are not so structured and are more creative, actually there's also quite a bit of progress. This is something that I personally find amusing, but not, which I don't spend a lot of time on, but it's when you start using computers to write poems and paint, or create pictures and in general create art. And there are actually some pretty interesting results on that front, which make me personally optimistic that creativity is not something that is somehow beyond explanation. Yeah? But if you look at going from something that is a specialized intelligence to a general intelligence, then the biggest difference is that the intelligence needs to be aware of all the context and all the connection between concepts. Yeah? And there's a wonderful comparison that they
I
made.
would like to keep it, because other people want to ask questions.
Okay, very short answer. The short answer to this is look for IQ shootout on different existing AIs with humans, and you will find that the strongest one, Google Brain right now, which as a general AI, yeah, is on the stage of a 5-year-old child approximately. Yeah? And that means somewhere around 47 IQ, if you compare to a grown-up person.
So now, very, very, very short.
Yeah, very fast.
And it has doubled the last 2 years.
Like I want to reformulate some questions that people have done, like the oracle, like of the Greek mythology.
thinking,
Yeah. No, the point is, how do you handle the Polanyi's paradox, and what do you think because that is a graph of next 20, 50 years, is kind of wrong, that graph. But so Polanyi's paradox and what do you think about patent copyrights when we look at the trend of the innovation growth? Because if I know that all algorithms will be the future, I would like to redistribute that knowledge. Otherwise, innovation is going down.
Mm-hmm. Okay, let's start with the paradox. Can you remind
We
me of that,
know
because I
more-
don't know that?
No, but then,
Yeah.
since this will take some time, you can ask the question, sorry, because
Okay, about the copyright, what do you think? In terms of, because we should decrease the years of the property of the ownership of the Google's algorithm.
I think if you're looking at the speed of innovation, yeah, there are some very nice logarithmic graphs which are showing how which impact we're getting in what amount of time. And this is increasing, the speed of this is increasing so much that I would argue that concepts such as 70 years of copyright and stuff like that are completely anachronistic. Yeah. And well, we only have them that long actually because of Disney, but that's another aspect. But I think we need to rethink intellectual property. Yeah. And also the question of who's going to profit from the automation of labor, and then we're coming to the whole area of citizen salaries and all kinds of
But this goes over above and beyond.
yes. Oh yes. We can continue this now.
Very quick.
Yeah. How can you be sure that that the AI can simulate human reasoning? I mean, I've been looking into some paraconsistent logics where there are more than these two
Yes.
truth conditions, true and false, both true and false, for instance. And one of the proponents of this kind of view thinks that this is how humans reason.
Well, there's, I mean, the first thing is I'm skeptical that we can build a logic that will follow human reasoning. Yeah. If I say that I'm optimistic, but I'm not sure, yeah, that we'll be able to simulate the thinking process, I'm more thinking about artificial neural networks and things like that, yeah, where things like reasoning and consciousness, they're emergent from exposure to the environment and learning through feedback. Yeah? But I don't think we can come up with logic that is describing all kinds of human reasoning. And this is one of the big advantages that we have over AIs so far. Yeah? We're very flexible. In one moment I can be a rigorous mathematician, and in another one I can be at home with my children, and the logics are completely different that are at work here. Yeah? And I mean, fuzzy logics and other parameters logic, there are many things, and they have uses, yeah? But I don't think that any of them are able to capture the logic of interacting with
My
a
ordinary
5-year-old
intelligence tells
child.
me that it's very interesting to go on, and you can of course discuss more with Peter, and we should thank for the nice talk.